So implicit differentiation, we've been doing this the whole time, and you haven't realized it. So this is pretty easy to move forward from, but it's essential that we have the chain rule under our belt, right? So so if I tell you to take the derivative d dx of y, what do I get? What's my answer here?
1.
1. And then I must consider, right? Sorry. What did you say? 1? No, y prime, right? Y prime. Yes. So the derivative of y is y prime. We've been doing that all the time, right? And what's weird about this piece is y is actually already the inside. There's kind of no outside function or no inside function, right? So in the same respect, if I take the derivative of w, right, where w is a function, what do I get? W prime, W prime. So I'm saying now, if I'm taking a derivative of a function that's unknown, I already know it's got to be prime. It's got to be y prime or w prime or g prime, right? So we've even done that in the product loop, right? If y equals f times g, right? We had f and f prime, right? G and g prime. So we've been doing this implicit differentiation the whole time, okay? So, but what if I said d dx of x?
Explain.
1. So when
1?
when we're taking our derivative of a function of x, we're using all our shortcut rules, right? But when we're taking a derivative of a function that's unknown, we're just keeping things in general. So that's got to be the derivative, or y prime, right? Or dy dx, right? All of these things mean the derivative. So if I take the derivative, and notice I'm always taking the derivative with respect to x. That's going to change in chapter 4, okay? But right now, we're always taking the derivative with respect to x. Sometimes the book will do with respect to t, but the variables are t. Sometimes the book will do with respect to theta, but the variables are theta. I usually change everything to x, just so it's a little bit less confusing at this point. But if I had an x squared, what's my derivative now?
2x.
Good. Times the derivative of the inside. Now I have a derivative of the inside. I have an inside function, right? The inside is x, the outside is an x squared function. So that makes me think, when I take the derivative with respect to x of y squared, what do I get?
Y squared prime.
Almost 2y y prime. So why didn't I get an extra piece of the derivative up here? Because there's no inside or there's no outside, right? It's such a simple function that I'm just getting the prime, right? So now down here I have y squared, so there's an inside of y. So I must first take the derivative of the general function. Y squared gives me 2y, x squared gives me 2x, w squared gives me 2w, right? But then I must take the derivative with respect to x of the inside function. And if it's anything but x, I get that function prime. Okay, implicit differentiation. Very, very simple. How we doing so far? So it almost is trust your gut on it, right? If it's in terms of x, do your derivatives as you know. If it's in terms of y, make sure you're thinking about the chain rule. We can't get rid of the chain rule for the rest of our mathematical careers, okay? All the way up to diff EQs if we're engineers, right? So explicit and implicit. What is the difference? We're used to seeing things explicitly, like y equals 1 over x, right? Notice on one side is my function, my general function, f of x or y. And on the right side, everything's in terms of x, right? If I cross multiply here, I get xy is equal to 1. And this is implicit. When the x's and y's are mixing, whether it's addition, subtraction, multiplication, division, etc., even exponentials, I want to be thinking about implicit differentiation, okay? So on the left side, if I take the derivative of both sides, whoops, ddx always for us right now, sorry. ddx of y should equal ddx of 1 over x, right? And what do we get on the left? On the left-hand side here, what do we get?
1 over x squared.
On the left-hand side. Y prime, right? The derivative with respect to x of y is y prime. I could keep it as ddx. That's fine too, right? On the right-hand side, what do I get? I'm sorry, Markins?
I'm lost.
You're not lost. What's the derivative of y? We've been saying it all the time. Y prime.
Y
Y prime. You're not lost. You're on Earth. Maybe Maryland. What's the derivative of the right-hand side?
One over x squared.
Almost. Negative 1 over x squared. Does anybody want to see that shortcut power rule? Anybody want to see that shortcut power rule?
Yeah, can you show it, please?
Yep. So if y equals 1 over x, that's x to the minus 1. And y prime is negative 1 times x to the negative 2. Right? We got to bring down the exponent and subtract 1 from the exponent. So there's my y prime equals negative 1 over x squared. On the right-hand side, we should get the same result, okay? Sometimes I can write a function that's written implicitly, explicitly. And then if I can do that, it's easier to do the derivative. But if I can't, I have no choice. I have to do implicit differentiation. So I'm going to take the derivative of the left-hand side, and that should equal to the derivative of the right-hand side. Well, what happens on the right-hand side? What's the derivative of 1?
0.
0. And on the left-hand side, I have a product, right? On the left-hand side, I have a product. My first function is x. The derivative is
1.
1. The second function is y. The derivative is
Y
prime.
nice, and I get a product loop. So I have xy prime plus y equals 0. And now my goal is sometimes to find the slope. If I want to find a slope, I just need to put in numbers. If I want to find the derivative, I need to solve for y prime, right? So if I solve this for y prime, what do I get? I get xy prime equals negative y, or y prime equals negative y over x. And I know that y is equal to 1 over x. So I get y prime is negative 1 over x, which again is negative 1 over x squared. Sometimes I can't solve things explicitly, right? So sometimes I cannot solve things explicitly. And in that case, I have to use this implicit piece, okay? And the key here, the little secret here is, if I ask you for a derivative, I want you to solve for y prime. But sometimes you can't. So I'm not going to ask you to solve for y prime if you can't, okay? But I can use even the most complicated version of it to find a slope, right? All I have to do is put in numbers for x and y, and then I can get a slope, right? So let me show you an example of that. So I've got an ellipse here. and my function is x squared plus xy plus y squared equals 3. And this is a real nice one to graph on Desmos. You cannot graph this one on your calculator because I cannot solve for y. This thing is stuck in implicit form. X's and y's commingling, and I can't separate them. Okay. So when I give you one of these on your second test, your chapter 3 test, I will give you a picture, right? So that it's a little bit easier to deal with. Let me just get a quick graph of this. So, Udi, are you there?
Yes, I'm there.
Okay. So I've got x squared plus xy plus y squared equals 3. And so it's a real nice nice little version of the ellipse. Desmos is so much powerful than those stupid calculators we have you using. I can see that 1, 1 works on the, look from the graph. I can see that 1, 1 is on the curve. Do you see that? 1, 1, right? So let's see if we can find a tangent line there at 1, 1. Okay.
Professor.
Yes.
I already looked on the test 3. Like examples that you have, I think was on the 2019 one. You have like a circle, but it's not a perfect circle, if I remember.
It's a cardioid, yeah, cardioid. Looks like a heart.
Yeah, it's the same style of question of this.
Yep. In fact, I would do all of the problems in section 3.5 that have a graph because I like them.
Okay.
Yep. So I see that 1, 1 is on the curve, and I want to get the tangent line, right? I want to get that tangent line. So what do I need for a tangent line? I need a point and I need a slope. To get a slope, I need the derivative. So we're going to do implicit differentiation here, right? So we're going to do the derivative of the left side, which is x squared plus xy plus y squared, should equal the derivative of the right side. And of course, the right side is easy, 0, right? What's the left side? Who's got the first part of the left side? What's the derivative of my x squared term?
Xy.
2x, nice. I'm going to wait on the product rule part, but I'm going to do the derivative of the y squared time. Who's got the y squared term? Who's got that?
Mr. Way.
2y prime, right? I have to do the derivative of the inside. I did the derivative of the inside on the x squared, but the derivative of the inside on the x squared is 1, right? So you could think of that, or you could just do when you're in terms of x, you could just do your derivative rules, right? And that should equal 0. I want to do this product rule again, right? So I've got a placeholder here. So I'm solving for this piece now, right? Working on the side, my first function is x. My derivative is 1. I already did this today, yes. Second function is g. G is y. Derivative is y prime. And again, I get that same loop, right? So now I have 2x plus xy prime plus y plus 2y y prime. Oops, that's xy prime, sorry. Going too fast, equals 0. 2x plus my product loop plus 2y y prime equals 0. Everybody with me? So I'm trying to stay really, really organized, right? If I have to do something on a piece of scrap paper, right? If I have to rewrite my homework. I'm solving for y prime here. This one I actually can do. This one I can solve for y prime. So on the test I would say, find me the general form of the derivative and then find me the tangent line, right? So I'm going to move my non-y prime terms over to the other side. So I get a negative 2x minus y. Everybody with me there? Anything without a y prime in it, I move to the other side. And then I factor out my y prime. Make sure I'm not going too fast here. I'm missing 2 students.
How did you just get the last part? Sorry, I was writing it down.
Yes, so I factored out. So if you see that if I it's always easier to see if I distribute the y prime back. You see I get what's on the left side. Was that tally?
Yeah, I see. Thank you.
Yep. And then I finally divide by that particular term, and I get my derivative. There's my general derivative. I mean, you could make it look a little bit better by saying negative 2x plus y over x plus 2y. That looks a little bit better to me. But my teacher would say, well, which one is better, and count the strokes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're both using the same amount of ink. So we'll say each is acceptable. Remember, as a computer scientist, I want to write as much as I can in the least amount of memory, right? So I'm always trying to minimize the amount of memory used here. Either one is fine. I like the second one better, but it doesn't really matter. And so there's our derivative. So we've got our point 1 comma 1, right? Our slope is going to come from negative 2 times 1 plus 1 over 1 plus 2 times 1, right? I'm plugging in the 1 for every x and y. So it looks like I get negative 3 over 3, which is negative 1. There's my slope. Everybody with me?
Yes.
And now my tangent line. I get y minus 1 equals negative 1 times x minus 1. Y minus 1 equals negative x plus 1. And I'm going to bring that 1 over. It becomes positive. Let me put this on my graph, okay? And I'll come right back to this page in a second. My tangent line at 1, 1 is y equals negative x plus 2, right? And there it is. How we do?
I'm doing good. Can you go back?
Yep.
So that I can finish program, please?
Say it one more time.
Yeah, can you zoom it a bit like out so that I can copy everything, please? Thank you.
Yes.
So what are those red marks that you put there on the...
I was just counting. I was counting the characters to show that both versions of my answer that I got had the same number of pen strokes. And that's how I'm going to decide should I simplify or not. I looked at my first version of y prime. I had 10 pen strokes. The second version, I had 10 pen strokes. So it's like saying to me, does it matter if I simplify this anymore? And the answer is no. If I went from 10 pen strokes to 7 pen strokes, then that's what I want. Okay.
Can you zoom out, please, for me?
So it's not too bad, right? And the main thing is if you have some function that's unknown, right? Like y or g or whatever I use, whatever letter I use, I want to make sure I'm using chain rule, and I want to make sure I'm looking for a y prime or a g prime, right?
Okay, can you go back up, Professor, please?
Go back up.
Yeah, zoom out, like, so that I can see everything.
Well, yeah, sure.
Thanks.
So in this case, when we're finding the slope, we
Marcus,
plug
you
in
can take a
y.
you can take a screenshot or take a photo. Say it again, Nahum.
So in this case, when we're finding the slope, we plug in for y too.
Yes, exactly. And you'll see in Calc 3. What are you studying? Engineering? No.
Yeah, computer science.
Oh, computer
Yes.
science. No, you won't take Calc 3. But in Calc 3, you'd have more than 2 variables. It's a multivariable calculus, but yes. So you're finding a derivative with respect to a certain variable, and then you're plugging in points for the other variables. Nice. Let's do the most difficult problem that I always put it on the test. So let's just jump right to the most difficult. Okay. Markins, you ready?
Yes, I'm ready. I'm good. Thank you.
Thank you. So I like tangent of x plus y equals x. This is my favorite problem. It's on every chapter 2 test or midterm I ever give. I change it a little bit, of course, right? Twist the mustache and do a little switcheroo on it. But as a trig masters of trig, you all know when I see a trig, what do I see? What do I see? What do I visualize whenever I see a trig? So with alpha equal to x plus y, right, I know that the tangent of alpha is equal to x. When I see that, what do I visualize? I have to get my crickets out, huh? I'm worried about...
Is it like sin x over cos x?
Good. I see identities. What else do I see?
Uh-oh. This one? Can I say it looks like that? Just guessing, I don't know.
I see a triangle. What kind of triangle?
Oh, like right triangle?
Yes. I see a right triangle with an angle of alpha. And tangent is telling me the ratio of sides. So what sides can I label there? 2 of them. I should be able to label 2 sides here.
Opposite over adjacent. So
Say again?
opposite over adjacent.
Yes, x over 1, right? Because x over 1 is x, correct? Now by Pythagorean theorem, I get the last side of the square root of 1 plus x squared. Does anyone need to see that? Pythagorean theorem for the hypotenuse.
Is it like a square good piece?
Exactly, a squared plus b squared, exactly. I could use a sum and difference formula here. Yes, you're right, but I stay away from tangent sum and difference or tangent to double angle, tangent half angle. It's just too much to do everything. So when I see a trig, I see a right triangle. Okay? So we're going to, most likely, every time we do something with a trig, we're going to have to refer to a right triangle. So let's get used to it. Okay? So let's go and do our derivative now. Let's do our derivative. Right? So I'm doing d dx of the tangent of x plus y equals d dx of x. Good. What's the outside function on the left?
Tangent.
Derivative of tangent is what?
Secant.
Yes, good. So secant squared, right? You were right, Markins. I said, what's the outside function tangent? Derivative of tangent is secant squared. Keep the cat in the box, and then multiply by what?
Sine.
The derivative of the inside, so x plus y prime. I'm going to just leave that for a minute, and then take the derivative of my right-hand side, which is?
1.
1. Nice. So now I'm ready to take my derivative of the inside. I get secant squared of x plus y times 1 plus y prime. Make sure you agree with that. Derivative of x is 1. Derivative of y is y prime.
Yes, I was thinking.
Remember, I'm solving for y prime, so it's pretty easy for me to divide by secant squared here. I get 1 plus y prime is equal 1 over secant squared of x plus y. Of course, I could rename that what?
Cos
Squared. Good. Cos squared of x plus y. And again, once remember, I'm solving for y prime. So I get y prime is cos squared of x plus y minus 1. And I could rename that what?
Is it sine?
Almost sine squared.
Sine square x plus y.
Almost. Just your coefficient's wrong. It's negative sine squared of x plus y. Right? 1 minus cos squared is sine squared. So this is negative sine squared. Notice here that I have the answer written I have the answer written in terms of cos
Oh, excuse me, Professor. Can you explain why is it like negative sine squared, please?
Yeah, 1 minus cos squared is sine squared. So cos squared minus 1 is negative sine squared.
Like Professor, just to see if I'm understanding. 1 over secant is cosine, this I only remember for a long time. And after that, we get the sine by getting cosine minus 1, that gives us...
Cos squared. Cos squared.
Yeah, cos squared minus 1, that's minus sine squared, yes?
Yes.
Okay.
So this one is in terms of sine. Let's do one more in terms of x. Who's got it?
What is it, Professor?
I'm asking for someone.
Yeah, but I don't know what you're asking. Like
In terms of x. It's going to come from here. What's my sine? Negative sine squared in terms of x.
So what's x again?
You said square root 1 plus x squared over x.
Nice. X squared, or how about this? Sine itself is x over square root of 1 plus x squared, but we're squaring that, right? It's sine squared from my triangle. So
why did you write it like that, Professor? Can you explain it to me, please?
I asked you to solve it in terms of x, right? So that means if I have a trig, I know how to get my x's from my triangle, from my ratio, right? So sine is x over opposite over hypotenuse, and then I square it, right? So it looks like I could simplify this a little bit, right? I can say that this is what, negative x squared over 1 plus x squared. Now I want it in terms of tangent.
So where did the sine go?
I got it from the triangle. Sine is, right, sine alpha is x, it's opposite over hypotenuse. Who's got my,
Is it 1 over x? No, I don't know.
no, that's cotan. Yes.
Yeah, 1 x over square root of 1 plus x squared.
Afsu? Question?
But yeah, the one that says in terms of x, how's that in terms of x and not in terms of alpha? Because
This is alpha, right? This is alpha, right? That's alpha, right?
Yeah.
So, but when we're looking at a trig, right? We're looking at a right triangle, right? And my angle we had was x plus y, but my sides were ratios of x, right? Because the original function was just a tangent, right? And tangent was equal to x, so I knew x over 1 for my opposite over adjacent ratio. Last one, in terms of tangent.
So first, square root of 1 plus x squared.
Yes, so I'm using this, and I want to turn it back into tangent. Well, the numerator is x squared, right? So what's x equal? Right here, what does x equal?
1.
No, x equals tangent of xy. So I get minus tangent squared of x plus y over
x squared.
1 plus tangent squared of x plus y. Right, so everywhere there's an x, I'm putting in a tangent.
Will you please explain it to me, please?
Yep. So x tangent is equal to x. So if I have an x here, I need a tangent, or tangent, because it's x squared, I need a tangent squared. So 1 plus x squared is 1 plus tangent squared.
Okay, I get it.
It's about as tricky as they get. Okay? About as tricky as they get.
So you're going to ask us to work them in terms of whatever.
Exactly. I'll say here's this implicit function. Find the derivative in terms of sine. Find the derivative in terms of cosine. Find the derivative in terms of tangent. Find the derivative in terms of x. Find a slope. Yep, anything like that. They'll get easier as you practice them. Okay? Want to do one more like that real quick? Yep.
Yeah.
Let's say sine of x plus y is equal to x squared. Instantly I see what? Because I have a trig. What do I see instantly?
Right triangle.
Right triangle. So sine of alpha equals x squared is going to give me this triangle, which I may or may not have to go back to. Okay? So I've got an alpha. I know my opposite side is x squared, and my adjacent side is, my hypotenuse is 1. Right? We agree sine is the ratio of opposite over hypotenuse, so x squared over 1 is x squared. Right? Easy now. A little confusing before, but it gets easier as you think. You do more. I need to find this other side by Pythagorean theorem. Can anybody tell me right away without doing any work at all? Square root of?
X to the power 4 plus 1.
Almost.
Root 1 plus x squared.
Nope. Almost. So let me call this side.
Oh, 1.
A. Okay.
Oh,
A squared plus x squared squared equals 1 squared, right? So a squared plus x to the 4th. Nahum, you had a piece of it there. So a squared is 1 minus x to the 4th, and a is the square root of that. Nice. Let's find our derivative in terms of x. Okay? Derivative in terms of x. Find y prime in terms of x. So derivative d dx of sine of x plus y should equal d dx of x squared. On the left-hand side, derivative of the outside is cosine. So I get cos of x plus y times the derivative of the inside, which is 1 plus y prime. Right? I jumped right to that one this time because it's very similar to the last question. And on the right-hand side, I get 2x. How are we doing here? So I'm solving y prime, right? So I'm going to divide both sides by cos of x plus y. So 1 plus y prime equals 2x times cos of x plus y. And then I'm going to subtract 1, right? So y prime is 2x times secant of x plus y minus 1. We okay there? No problem. Well, it looks...
Can we just... Oh, sorry.
Go ahead.
Can we just plug in the... adjacent over opposite?
Yep, anytime you want, absolutely.
Plus x plus 1.
Exactly. So y prime is 2x times the square root, times 1 over the square root of 1 minus x squared minus 1. And then I simply want, this is pretty, it's okay. Right? This is definitely okay. So this is 2x over square root of 1 minus x to the 4th, right? Sorry.
Yeah, I was thinking.
Yeah, minus 1. So that's a good answer because it's solved in terms of x, right? There's only x's and coefficients on one side. That's what it means to be solved for x. I could get an LCD here, but it doesn't help at all. Right? This doesn't really help, but I could certainly say that the answer is here. Of course, if I count my pen strokes here, this one's better. But I want us to get in the habit of, if you have more than one fraction, get me a single fraction. Okay? That's kind of one of our themes, right? If you have more than one fraction, turn it into a single fraction and factored. How we doing? Chris shaking his head. He's like, no, I'm not doing. You'll get used to it. You have to practice. That's all. Practice. Should we look at another one? Where's my book? Oh, there it is.
So, and this question would have been, get y prime in terms of x.
Exactly. Yep, that's what I had said, right? So I gave you a function that's clearly implicit, right? And then we want to find the y prime. The main thing is when you see a trig, you're gonna instantly think of a right triangle. In fact, we're going to take it one step further next section. If you see an inverse trig, what do you see? If you see an inverse trig, what do you see? If I say to you y equals the arctan of x, right? Or y equals inverse tan of x, what do you see? Trust your gut. Go ahead, Noah.
We just switch the numerator and denominator?
Nope.
Yes.
Are you thinking of inverse functions?
Is it circle?
Say again, Marcus.
Circle?
Nope.
Rectangle?
Almost. Something before the rectangle.
Square?
A trig. I don't think in terms of inverse sine or inverse cosine or inverse tan. So what do? I switch them, right? I take the inverse function. So if I see an inverse tangent, I see a tangent. If I see a tangent, I see a triangle, right? So we're just adding one more step to this theme. If I see an inverse trig, I see a trig. If I see a trig, I see a triangle. Most likely I'll have to go back to the triangle in a problem whenever I'm using trigs. Okay?
Professor, what is the difference between trig and a right triangle?
Nothing. Absolutely nothing. That's how we learn trig, with right triangles, right? The trig's just to define 6 possible ratios, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, etc., right? 3 others. So they're identical to each other. In fact, they're so special, right? Trigs are so special that's why we came up with them. We came up with the trig definitions because it didn't matter how big the triangle was. If the angle stays the same, the ratio stays the same, right? And so that's why it's so special, right? We have proof that the ancient Egyptians knew it and knew the Pythagorean theorem long before Pythagoras was around, right? But Pythagoras published it. So, stole it, proved it, published it. Evil people. But supposedly, Pythagoras studied with the ancient Egyptians, or he was at least allowed access to, some of their secrets. We don't know how he did that. Supposedly he had some magical powers. Or have you ever heard of numerology, where you can tell something about your personality, like if you're a Pisces, yada yada, when you're born, but also your name number. Like I would be Rob Kuhar, and for every letter in the alphabet there's a number, and then you add up all of those digits till you get a single number, and that number tells you about your personality. It's pretty cool. It's Pythagoras. Pythagoras believed everything could be described, everything in the universe could be described by integers. Let's do another one. This is a pretty cool called the Folium of Descartes. So we'll do another one with the graph, and then we'll do another one with the.
This is all in 3.5.
Yeah, 3.5. Yeah. This is the Folium. Of Descartes. I don't think it's Rene Descartes, because there would be no S. Was there? Is there Rene Descartes? Yes, there is, isn't there? I forget. Doesn't matter. It's a pretty cool curve. Let's see if I can get a decent picture of it here. That's pretty good. And notice that at 0, 0, there's a vertical tangent line and a horizontal tangent line. I guess it would be nice for me to graph this in Desmos instead of my lane picture. It's x cubed plus y cubed equals 6xy. And I'm obviously interested at the point 0, 0. What do you think I'm going to see? Let me graph this. X cubed plus y cubed equals 6xy. Now, one of the things that's interesting about this is not a function, right? We've got issues here, right? So not a function, so how do I do anything with it? Well, implicit allows me to. Changing things to polar allows me to. Changing things to parametric allows me to. So there's lots of little tricks that we've been learning throughout pre-cal to allow us to work on this thing as if it were a function, even though it isn't. So at 0, 0 is where I'm really interested in here. I think the book asked you about something else, but 0, 0 is where I think it's interesting, right? Because can you see the vertical tangent line? So what does that mean about the derivative if I have a vertical tangent line? What's the slope there? If there's a vertical tangent line, what's the slope? It's x equals 0, right? X equals 0. There, that blue line is the vertical tangent line. What's the slope of that line?
Infinity.
Infinite, yeah, infinite. Exactly. So the derivative doesn't exist at 0. At 0, 0, the derivative doesn't exist, which means what is 0, the numerator or the denominator?
The denominator.
The denominator. The denominator. When the denominator is 0, it doesn't exist, right? Can't do it. Can't divide by 0. But at y equals 0, I've got a horizontal tangent line, right? In green there. At y equals 0, I have a horizontal tangent line. For the derivative, what's 0 now? The upstairs or the downstairs?
Numerators.
The numerator, right? The numerator. So it's kind of interesting. And I'm losing I'm dragging a little bit, am I? Picture, sound, anything?
It's good.
Okay. So I know Desmos is constantly running, so it's eating up my my memory here. But let's take a look at our derivative here, right? Let's do d dx of x cubed plus y cubed and d dx of 6xy. Good. Who's got the left-hand side for me?
What, 3x squared
Good.
plus 3y prime.
3y squared y prime.
Yeah.
Nice. The next piece I need a loop, so I'll do 6x and 6y and y prime. So I get 6xy prime plus 6y for my product loop. I'll let you catch up there if that was too quick. I want to solve this for y prime. Is everyone okay here?
Can you go back and deploy that code again, Professor?
One more time.
Deploy that code. Can you go back in it?
Right here.
Last one.
Yeah, right here. First function is 6x, right? Derivative is 6. Second function is y. Derivative is y prime. I want to solve this for y prime. I have two choices. I always am trying to minimize the number of negative signs I have. So on this one, it doesn't matter. I'm going to move my y prime terms to the left. So I have 3y squared y prime minus 6xy prime. And my non-y prime terms to the right. So I have 6y minus 3x squared. Make sure everybody's with me there. Now I can factor out a y prime. I get 3y squared minus 6x, right? And I'm going to divide by that term to finally get my y prime. This is one of the rare cases where I can solve for y prime easily. It doesn't always happen. In this particular case, I can solve for y prime. You can't always do it. If I ask you to find me the slope, I don't care about the derivative. If I say find me the derivative, then I want you to solve for the derivative. But notice what happens at 0, 0 here, right? Y prime at 0, 0. Look at what happens. I get 0 over 0. We're going to make that connection to the graph. I get a vertical tangent. I get a horizontal tangent. Right? When the numerator is 0, I get a horizontal tangent line. When the denominator is 0, I get a vertical tangent line. Nice. We're doing well. We're a class ahead at least. So we're doing really well. You can start. We only have one more section of material that I'm going to test you on. At least that's what I'm thinking now. We'll do that Wednesday. Friday, we'll do 3.7, which is log derivatives. And I'll show you some problems but I won't put any on the chapter 2 test. That's what I'm thinking now. I'm just trying to make things easier, trying to cut some things out. That is something you need in Calc 2, but do I have to test on it? No, I don't have to.
Can you please scroll up a little bit, Professor, please?
Professor,
Yes.
what things previous to this class that like wasn't on the first test that will be on this test?
One more time. Didn't get it.
I see that my question is strange. Like, what subjects we didn't have on the second exam? No, Matt, on the exam from chapter 2 that will be on the chapter 3, but like...
No, I won't do that. I won't. If I ask you for anything from chapter 2, it would have been on the test.
No, like, because we learned like the chain rule and things like that. Which things other than the chain rule we learned before today? Like, that is, will be on this test.
Shortcut derivatives, chain rule, trig derivatives, 3-4 was 3-4 was chain rule, sorry. 3-5 is implicit, 3-6 is inverse trigs.
Okay.
Professor, so the inverse trigs like arctan and stuff like that, right?
Yeah, arctan, arcsine, arccosine. I don't put the other inverses on.
And we're doing that next class, or?
Yeah, next class. Yeah. Let's do one more and then quit. Okay, so this is in 3.5, number 13. I've got e to the x over y equals x minus y. So we want to find the derivative. We want to find y prime here. Okay. So using implicit find y prime, right? So we're going to take the derivative of both sides, e to the x over y prime should equal x minus y quantity prime, right? You can see I have two ways of writing that I want to take a derivative. A ddx, right? That's an operator, right? So if I have y equals 4 and I use the operator square root, I get square root of y equals square root of 4, right? If I have y equals 4 and I use the operator ddx, I want ddx of y equals ddx of 4, okay? So you have to show me that. This is just a little side note on some of your notation. If you're taking a derivative, tell me what you're taking the derivative of. If you're taking a square root, right, etc., you know what I mean now, right? So what's the derivative of the right-hand side? That's pretty easy, right? What's the derivative of the right-hand side here?
Is e over x over y.
Right-hand side.
And side negative y prime.
Okay, negative 1. The derivative of x is 1. The derivative of y is y prime, right? Remember that y is we're thinking we don't need the chain rule there because there's no inside. How's that, right? On the left side, I get e to the exponent times the derivative of the exponent, right? The derivative of e to the x is e to the x, right? But it's not an x inside, it's a cat inside. So derivative is e to the cat and then cat prime, right? Inside prime. I need a quotient rule there, right? So it looks like I get e to the x over y times y minus xy prime and it looks like I can pretty easily solve for y prime. Is everybody with me here?
Professor,
Yes.
we over y squared.
Thank you. Oh, you saved me big time. Thank you. I've been like, what's wrong? Why can't I figure it out? I always forget. Even as a student, I would forget the downstairs squared. So I'm going to solve this for y prime. It's kind of nasty, right? Kind of nasty, but let's see what I can do. There's not much I can do. Really, there isn't too much I can do. So I guess I'm going to just distribute, right? I'm going to distribute. I can't really see anything else. So I have e to the x over y times y over y squared minus e to the x over y times xy prime over y squared equals 1 minus y prime. I'm just trying to isolate terms with y prime in it, right? I'm not going to simplify too much yet. I want to get all of my y prime terms on one side, trying to minimize the number of negatives. Doesn't matter what I do here, I'm going to still have two negatives. So I have y prime minus e to the x over y times x y prime over y squared. And on the other side, I'm going to get 1 minus e to the x over y times 1 over y. Right? One of those y's reduced there. Oh, that's a y prime. That's a y prime, not a y squared. Thank you. And why did I put a 2 there? Because I was going to say over y squared. So my head is jumping ahead, y squared. Right? And I wrote that for my y instead of y prime. I can factor out a y prime, and I get 1 minus e to the x over y times x over y squared. You can see they're just messy, just nasty. You just got to be patient, try problems a couple of times. So I finally can solve, I can say y prime is 1 minus e to the x over y divided by y over 1 minus x e to the x over y divided by y squared. And it's pretty obvious here that I'm going to clear fractions with y squared. So I get y squared minus y e to the x over y over y squared minus x e to the x over y.
So do the top one, is it supposed to say y squared or y prime?
Thank you, y squared. What's the sense of making a mistake if you can't do it more than once, right? I can do something else. I don't necessarily have to, but it'd be interesting to look at it and see what happens. And that is that I know what e to the x over y is. It's x minus y, right? So I'm going to take this e to the x over y and substitute it with an x minus y and see if anything interesting happens. So y squared minus y times x minus y over y squared minus x times x minus y. Something could happen here that is interesting. I'm not sure yet. Y squared minus xy plus y squared. Is that right? Yep. And then I have a y squared minus x squared plus xy. It's not really that interesting. Two y squared minus xy over y squared plus xy minus x squared. I don't know if it's any better than this one. But I mean, I could factor out a y upstairs. which is going to keep putting me in a circle. So this one's fine. And that's the one where you would look in the back of the book and see, and make sure we're doing that, please. Make sure you're correcting your homework by looking at the answers. So on this one, we're going, well, let me see if the answer has an e to the x over y or not. Is it just x's and y's, or is there an e to the x over y? And then we know which one we want, right? Oh man, I guess that wasn't that easy, but I think it'll be easy as you keep working on it, okay? As you keep working on it, it will become easy.